Hi there, welcome back to the formulaic approach. Now in this video, we are going to talk about linear momentum and collision. If you have not already, do want to subscribe to the channel. Our focus in this video is going to be collisions and their types. So it is the continuation of our video on dynamics. If you have not seen that video, I'll link it in the description. Do want to check it out. Now in that video, I've already introduced you to what change in momentum is. But first, let me give you a real-life view of what momentum is that you have probably experienced before. Now, if you are standing at the edge of a road, you probably have experienced this before, at the edge of a busy road. Now, if a car, a huge car, passes beside you, you're going to feel something as if you were being, you're going to feel something like a force that would cause you to almost move, right? In fact, if someone that is walking speedily, walking fast, moves beside you in an opposite direction, you notice there's one kind of breeze that's going to blow that will make you feel like that person is walking too fast or almost hit you, that kind of thing. Do you understand? So that is basically momentum, the momentum of the person. So actually, we describe momentum as the product, denoted by P. It is the product of the mass of a body and the velocity with which the body moves. That is what momentum is, the product of the mass of the body and the velocity vector with which it moves. So you see, it is also direction sensitive, momentum. That's why it's a vector, all right? It's a vector quantity. So given this formula, we know that the unit is going to be kilograms meter per second, okay? This is going to be the base unit, All right, but now let's now build it up from dynamics. So we already know that we are studying under dynamics the forces that cause motion, right? Now we describe force as the product of the mass of that body that is experiencing the force and the acceleration produced by the force, usually in the direction of the force. Usually in the direction of the force. Now, I am saying that the force is mass times acceleration. And recall that we said acceleration is also what? The change in speed per unit of time, right? So we have that acceleration is v minus u over t. By the time we substitute this into that equation, it improves to m into bracket v minus u over t. By the time we do basic algebra, of course, multiplying, we're going to have this times this, force times time, ft, is equal to m, open the bracket with this, mv minus mu, right? So what this means is that there is a change in momentum. Momentum is mass times velocity, recall. So mass times velocity and mass times velocity. But this is mass times final velocity minus mass times initial velocity. So there is a change in momentum here. So we'll call this change in momentum. Is that clear? I'm going to recap how this is for you. Now, there is also here impulse. Now, this component of the formula is change in momentum. And we found out that it's actually equal to this component, which is called the impulse. So, impulse we describe as the product of the force, of a particular force acting on the body, and the time over which that force acts on the body. Is it clear? So that is what impulse is. So it turns out that the impulse is exactly equal to the change in momentum that a body experiences. All right. So having said all that, we know where momentum is practically coming from. Now let's talk about collisions, which is our focus. Collision. Now what does collision mean? When bodies is from the word collide, right? So when body moves and they come together and get to actually hit each other. So they impact relative forces on each other. So the force may either stop or improve the motion of the body. But the point is that it changes the motion of it impacts the motion of the body in a way, okay, such that the bodies may have a new velocity, begin to move with a new velocity or otherwise. Is that clear? So for example, when two bodies collide, think of this case where two cars are moving and they get to collide on the road, for example. Now when they collide, what happens? You practically notice that sometimes one may stop, the other may almost fly off in a different direction, and other things like that. So that's to show you that that impact that they had on each other had caused something to happen. Is that clear? Has caused a change in the motion of that body. Now listen, there are two types of collision. We have the elastic collision, and the inelastic collision. Now, before we start discussing them, I want you to know that these are the two examples between two extremes. Okay, there are two extremes. What are the two extremes? We have perfectly elastic and perfectly inelastic. But I want you to know that anytime we talk about elastic collision, we are basically referring to perfectly elastic collision because that's easier. Perfectly elastic collision is almost the case. Okay, almost the case. Of course, there is almost no perfect system in the universe too. All right. So, but in an isolated condition, elastic collision is almost perfect, almost perfectly elastic. But the inelastic collision is not always perfect. Is that okay? So that's why we will separate them in this video. All right. So elastic case, very easy, is what we're going to deal with first. Now, when do you call collision elastic? Collision is elastic, physically speaking, when the two bodies that collide, after colliding rather, change direction. Okay? They move apart when they collide. That's the definition of something being elastic. You know, two balls, for example, football. You have a well-pumped football. You have it on the pitch, it's staying stationary somewhere, and you kick another ball towards it, provided that you have a straight leg. Probably like you can play ball like me. So if it hits that other ball that is stationary, what will happen is that it will move apart. Exactly, they will move apart. That ball is going to move. That next ball will not move with the first ball that hit it. Exactly, will move apart. Exactly. So I'm saying that in elastic collision is primarily physically described as motion where the two bodies move apart from each other with new velocities whenever they hit each other. That is what physically describes elastic collision. So, but dynamically, actually, we see that in elastic collision, it is the sort of collision where both momentum of the body, both momenta of both bodies, the plural of momentum is momenta, exactly. So both momenta are conserved, as well as, so both the momentum or the momenta of both bodies, both momenta, and the kinetic energy of both bodies and kinetic energy are conserved. Okay, so this brings us to the principle of conservation of linear momentum and principle of conservation of energy. Okay, now in elastic collision, keep that in mind, that both momentum and kinetic energy are conserved, and that is what primarily separates elastic from inelastic. In inelastic collision, only momentum is conserved, because momentum is always conserved in a given system, in any system at all. So, but the kinetic energy in inelastic collision is not conserved. Is that clear? So, but in elastic collision, both momentum and kinetic energy are conserved. Keep in mind, I'm speaking of perfectly elastic. Is that clear? So, both momentum and kinetic energy are conserved. Now, let us give the notion of that in the perspective of a diagram so that you can see what I mean. So when there is a body, the examples of particles or things that engage in perfectly in elastic collision are tennis ball on the table, tennis ball, okay, or ping pong ball, right? That's what they probably call it in China. I don't know. So tennis ball, football itself with another football, billiard ball, okay, I don't know how to spell it, billiard balls on a snooker table. You know pool, right? The billiard balls. Gases, yes, that's a very typical question. gases in a container. They engage in what? In random haphazard but yet elastic collision. Perfectly elastic collision. So now say there is a particle here, for example, I'm going to use the billiard ball. So a billiard ball has its initial mass, is moving in this direction, M1 moving in this direction, U1. Is that clear? So, and before collision, it was moving this way. And this other guy, let's assume this other guy is actually moving in this direction. Now keep in mind that I have told you that this thing is also direction sensitive, because when we solve questions, you are going to see how we alter direction. So usually, keep this in mind first. Usually, when one body is moving in opposite direction to the other, we designate one direction as positive, the direction of the first object, that's what we like to do, as positive, direction of the second object, once it's opposite to the first, the direction of the velocity of the second object is designated negative. Is that clear? So, and usually because in elastic collision, they will move apart again. So we might not really change the signs. I'll tell you why. I will show you how. Is that okay? The signs might not really change. Now, but let's first get into this to show you what is happening. Now, this body is moving like this. This other body, M2, is moving in this direction with velocity U. Now, as they are moving, this was before collision. Now, after collision, what will happen is that this body will move apart once they hit each other. Mass 1 will move with a new velocity 1, apart from mass 2, which will also move with a new velocity v2. Is that okay? So this is after collision. This is before collision, this is after collision. So, and keep in mind the principle of conservation that I said. Principle of conservation of linear momentum. Now, what is this principle saying? This principle states that the momentum before collision is equal to momentum after collision. The principle, another way to state is that no momentum is lost before and after collision. The principle is also saying that total momentum is always conserved. Is that clear? So you see, you heard the three forms in which I presented the principle. The momentum before collision and after collision equal. Momentum is not lost, and total momentum in the system is conserved. All right. So if that's the case, then how do we write that mathematically? Mathematically, we are saying that the momentum before collision is going to be product of this mass. Total momentum is m1 times u1. That's the momentum of m mass 1 of body 1. So total momentum before collision will be this momentum plus this momentum. Does that make sense? It should be equal to the total momentum after collision, which is m1 v1 plus m2 v2. This is what is practically stating the principle of conservation of momentum. Now, what is principle of conservation of energy saying? It's saying that no energy is lost in the system. At least in this case, we are talking about kinetic energy. That total kinetic energy is conserved. So the principle of conservation of energy is saying what? Total KE is what? Conserved. Total KE is conserved. So if total KE is conserved, then we write this equation in terms of KE as well. So here we have, remember that KE is half mv squared. Remember that, right? So we're going to write this like that. That this one will be half m1 u1 squared, exactly, because it's the initial velocity squared, plus half m2 u2 squared should be equal to half m1 v1 squared plus half again m2 v2 squared. Is this clear? All right. So this is what the two principles are saying. Now let's bring in some. Bring out some equations that can tell us some things that happen with systems when they collide, when bodies collide. Now let me show you something. Now, given these equations, these two equations, What if body 1 was the only one moving and body 2 was at rest? So look at this case where what? Body 2. If body 2 is at rest, remember, when a body is at rest, the initial velocity is what? 0. So what does that mean? That this body is at rest, it's not moving. What happens is u is 0. This body comes to hit it. Now what would happen? That's the case we want to examine here. And we'll examine 3 other conditions like it. It will help you. This part now, listen to this part very well because it will help you to understand solving questions. There are some theoretical questions that you don't need to solve before you need to touch your book or solve something before you attempt them. If you understand this thing I want to explain. Now, for this guy, where U2, body 2 is at rest, so U2 will be 0. It means that the total momentum, so body 1 is going to hit body 2 still. So what will happen is that the total momentum before collision will be just the momentum of the body 1. Because that's the only one that is moving, right? So we'll have that M1U1 should be equal to the total momentum after collision, which is M1V1 plus M2V2. I mean, keeping in mind, although that U1 is going to be greater than the two velocity, V1 and V2. But of course, this makes sense, right? If U2 was stationary and U1 was the only one moving. So we are U2 stationary. Okay? Now, like I was saying, now let's do some manipulations here. Since M1 is here and M1 is here, what we want to try to do is let's write an expression for velocity in terms of masses. If we're able to see just the masses that's what we want to try to do. If you can get the mass, if you are given just the masses, we want to be able to determine what the values of the velocities will be, or what will happen to the velocities of the body. That's what we want to do with these equations. So follow me. Just stay with me. Let this guy come here. By the time this guy comes here, we're going to have M1U1. Here becomes minus M1V1 equal to M2V2. Keep in mind this will be positive. Why? Because V1 is very much less than U1. Okay? So, that's the way it is. So that's the way it is. This is the case. So from here, we can already tell that M1 is common between U1 and minus V1, right? If you use this to open the bracket, you get this back, right? So this is M equal to M2 V2. Let's call this equation 1. So stay with me. Now, using this, the total kinetic energy will also be this. Total KE, total kinetic energy, will look like this. You know that this one is 0, so this entire thing here will be 0, right? So we have half M1U1 squared plus 0 is equal to half M1V1 squared plus half M2V2 squared. If this is true, then we can bring this guy here as well, so that we have half M1U1 squared minus half M1V1 squared is equal to half M2V2 squared. If this is true, likewise, what will happen is that we can factorize here. How do we factorize? What is common? Half M1 and half M1. So we have half M1 is common. Between, by the time it leaves here, it remains U1 squared minus this one leaves here, V1 squared is equal to half M2 V2 squared. So if this is true, then you notice half can take care of half, right? So that we're left with M1 into brackets U1 squared minus V1 squared is equal to M2 V2 squared. Are you with me? Now notice that this is difference of two squares. In maths, if I have a squared minus b squared, it is the same as a minus b multiplied by a plus b. Because if you expand these brackets, you distribute these brackets like this into each other, what you later get is this guy. Exactly. So I want to express this difference of two squares like this for this guy. U squared minus V squared is just like A squared minus B squared, right? What you will do is write the first expression minus the second expression, then write the first expression again plus the second expression. So the same way here we have M1 into brackets U1 squared, U1, sorry, minus V1 times U1 plus V1. Is this clear? So this, if you open this bracket, you will get this back. Exactly. So it's equal to M2V2 squared. Now, let's call this our equation 2. Now, look at the manipulation I'm going to do. I'm going to divide equation 2 by equation 1. Okay? So where's my equation 2? M1 U1 minus V1 U1 plus V1 equal to M2 V2 all squared. Divide it by equation 2, by equation 1 rather, which is M1 U1 minus V1 is equal to M2 V2. Now, stick with me. You see this, that something can already happen here. This guy can take care of this, right? M1 can take care of M1, right? M2 takes care of M2, right? There's no square here, sorry. There's no square. So V2 can take care of one of the V2s, right? So what do we have left upstairs? We have U1 plus V1 is equal to V2. Or more like saying that V2 is equal to U1 plus V1. So let's call this equation 3. We are on equation 3. So this one is that we are writing the velocity of V2 in terms of U1 and V1. Is that clear? So now, let's now substitute this guy into the equations we had initially. Let's substitute it. Now, by the time we substitute this, let's substitute this into equation, let's substitute into this equation 2. Okay? So, since V2 is already given here, right? V2 is already given here. So, what is equation 2? Substitute equation 3 into equation 2. What does equation 2 say? It says M1 into brackets U1 minus V1, then U1 plus V1 is equal to M2 V2 squared. M2 V2 squared. And V2, recall, we just said that V2 is U1 plus V1. So we have U1 plus V1. So by the time we substitute it there, it becomes M1 into brackets U1 minus V1, U1 plus V1 equal to M2 into brackets U1 plus V1 squared. Does this make sense? If we square it, it means it's appearing twice, right? U1 plus V1, like this. That's the square. Makes sense? So what you will do is divide both sides by U1 plus V1. So to cancel here, to cancel here. One will cancel here, one will cancel there. Then what we have is M1 into brackets U1 minus V1 is equal to M2 into brackets U1 plus V1. Okay? So from here, let's open up the brackets. We have M1 U1 minus M1 V1 is equal to M2 U1 plus M2 V1. Now, let's write an expression for V1. And how do we do that? Let's collect V1s together. Let's bring this guy here and bring this guy here. This one becomes M1 U1 minus M2 U1 is equal to M2 V1 plus M1 V1. So V1s are now together. So we have that, I can flip it over, it becomes, or let's just factorize this. V1 is common, so it becomes V1 into bracket M2 plus M1. I just brought this guy here, is equal to this guy. So what is this guy here? U1 is common here too. So let's bring out U1 into bracket M1 minus M2. If you divide both sides by M2 plus M1 over M2 plus M1. Now, this takes care of this. So V1 is equal to M1 minus M2 over M2 plus M1 times U1. Let's call this equation 4. Now, I'm going to use, this is our first equation that makes sense in the interpretation that we want to make. Now, you see, you see this guy is going to tell us something about the bodies and about how their masses impact the speeds of the body. That's what this equation is going to tell us. And this is the first equation. Now look at the second equation here. This same guy here, let's write it from equation 3. From this equation 3. From 3. 3 says that V2 is equal to U1 plus V1. So we can write V1, write the expression in terms of, the expression for V1 rather. So V1 here is going to be equal to V2 minus U1. So let's call this like equation 5. So we'll now substitute this one too into a new equation. We have substituted into 2. Let's substitute into 1 now. So substitute 5, equation 5 into 1. So what is 1? 1 is M1 U1 minus V1 equal to M2 V2. Just stick with me, you will understand. By the time I begin to now explain what these equations are for, you now understand why it was necessary to derive them. Just stick with me. So M1, we want to substitute for this guy, right? For V1, okay? So what will happen is that we'll multiply through. Let's maybe open the bracket here. If we open the bracket here, what will happen? To become M1 U1 minus M1 V1 is equal to M2 V2. So we can now substitute for this guy now. This guy is this, right? So it becomes M1 U1 minus M1 into bracket. V1 is V2 minus U1. So it becomes V2 minus U1 equal to M2 V2. So from here, we'll have that M1 U1 minus M1 V2. M1 V2. Minus times minus plus M1 U1. M1 U1 is equal to M2 V2. Are you following? So from here, we can collect these guys together. It becomes M1 U1 plus M1 U1 to give, let this guy go there, to give M2 V2 plus M1 V2. Why did I take that guy there? Because they have V2 in common. Is that clear? So from here, M1 U1 plus M1 U1, that's 2 M1 U1, right? 2 M1 U1 is equal to, V2 is common here, V2 into bracket M2 plus M1. Is this clear? So if that's the case, divide both sides by M2 plus M1 or M1 plus M2. This goes here, M2 plus M1. So V2, we have written an expression for V1. So an expression for V2 now is 2M1 U1 over M1 plus M2. Okay? Or M2 plus M1, you know it's the same, commutative. So this is equation 6. Now let's now begin to interpret things. Now, first, what do these equations tell us? The first thing that these equations tell us is that V1 can be positive or negative depending on the value of M1 and M2. When with V1 be positive. This is a case, recall that this is a case where body 2 was not moving at the beginning. It was only body 1 that was moving. So the velocity 1, which is the new velocity of body 1, remember V1 is for body 1, V2 is for body 2. U1 is for body 1. There's no U2 here because the body is not moving initially. So if mass 1, the mass of the first body is greater than the body it wants to go and hit. Let me recap that. If M1 is greater than M2, that is, the body that is moving is greater than the body that is not moving. So the body that is moving went to go and hit the body that is not moving. And that body that was moving initially is greater in mass than that body that was not moving. What does that tell you? It means that V1 will be positive if M1 is greater than M2. And you can try it here. Let's use 20 kilograms for mass 1 and 10 kilograms for mass 2. What will you get? You get a positive answer for V1. Is that clear? But when mass 2 is greater than mass 1, what does positive answer mean for velocity 1 first? The positive answer means if it hits that guy that is stationary, that velocity 1 will continue in its direction of motion. It will hit it and still continue in its direction of motion. Is that clear? It will hit it and continue in its direction of motion. That's when V1 is positive. But V1 will be negative if M2 is greater than M1. And let's check it. If this one was 10 and this one was 20, to give you minus, right? Now, what does that mean? It means that if a smaller object moves and hits a bigger object, it will change its direction of motion. Is that okay? So velocity becomes negative. That is, it changes its direction. Is it making sense to you now? Now, what does that tell you here? What does this equation tell you here? So this is what equation 1 tells us. Now, equation 2 tells us about body 2. That the velocity that body 2 will get, what will happen here? If M1 and M2 are the same, if M1 were exactly equal to M2, it tells you that, what this tells you here is that if I use 10 here, and I use 10 here, for example, 10 minus 10 is what? 0. So 0 over this is 0 times this is 0. So that V1 will be what? V1 will be what? V1 can also be what? 0. Yes. When will V1 be 0? When M1 equal to M2. What does that tell you? It means that if the two masses are the same, that when the first mass hits the second mass, that the first mass will stop moving and the second mass will be the one to continue moving now. Is that clear now? The second mass will continue to move, but we don't know yet because we have to examine for V2 now to know what will be the velocity of that body that is moving. So let's check. If M1 were greater than M2 in this case, we like to look at where it is very much greater than M2 and where it is very less greater than M2. So let us call those conditions. Let's call them conditions of, let me rename them as condition of 1. Condition A is a condition of equal masses. So when the masses are equal, I have told you just now that V1 will be 0, V1 will be 0. Now what will happen to V2? Masses are equal, remember? If I put 2 times, let's say I use 10 kg, objects of 10 kg that are elastic, it will become 2 times 10. So it will become this equation for V2, it will become 2 times 10. Now U1 does not change. We want to know what will happen to U1. So let's leave it as U1 over 10 plus 10 again. 10 plus 10, that's 20. So 2 times 10, 20 over 20 times U1. So what does this tell you? It tells you that if the masses are the same, that V2, that is the body 2, we get the exact velocity with which the first body was moving. You remember that I said that if the masses are the same, that this equation 1 tells us that body 1, once it hits the object, it will stop moving. So the new velocity will be 0. But body 2, according to that case, according to this case of equal masses, body 2 will begin to move with the same velocity that body 1 was moving. V2 will be equal to U1. Is it clear now? So what this is saying for equal masses is just that they will exchange what? Velocities. Is it clear now? They will exchange velocities. And that makes sense, right? You see it's making sense now. Now let's look at a case where there are unequal masses. Now unequal masses is easier, the best way to understand it is where there is extreme difference. Where, for example, M1 is very, very much greater than M2. And we also see case 2, there is BII, where M2 is very, very much greater than M1. Now, in this case, what will happen to the velocities? Now, where M1 is very, very much greater than M2, for example, think of a case of a cannonball. Let's say this one is a cannonball. You know a cannonball, right? And you know a football. The cannonball is, if you have seen the movie Bahubali or one of these war movies, you would have seen them throw a huge ball of fire. They will light it up, and they will be launching it into the city that they want to destroy, you understand? There was one war like that too. They launched it. I started to, I needed to activate my power. I started jumping up and kicking the cannonballs back. Then I was kicking it back. So more on that later. If you want to know the story, I'll tell you this full story later. So the point is, cannonball and football. So that cannonball, you can imagine, you know how big it is, right? We have seen that movie I mentioned before. Very huge ball compared to the size of a small ball. Let's say that small ball is as heavy as even having up to 1 kg. Cannonball will be like 1,000 kg, a ton, and football is 1 kg. So this is where mass 1 is very, very much greater than mass 2. So now let's see what will happen in this case. Easily, let's come to this place. Let's plug in the values. If we plug in our values into this equation, you will notice that V1 will be equal to M1 greater, which is 1,000 minus 1 over, recall that U1 is not changing. We want to know what will happen to U1. M2 is 1 plus M1 1,000. 1,000 minus 1 is what? 999. This plus this 1,001. What's the difference? It's almost 1, right? 999 divided by 1,001 is 1. It's approximately 1, right? So this is 1 times V1. So what does that do? This tell you? This is telling you that V1 will be almost equal to U1. That is, when a huge mass, so think of it this way, that one small ball is somewhere, a ball is staying somewhere, and a huge cannonball was rolling towards it. By the time it gets to this ball, what will happen? It will hit the ball away and will continue with almost the velocity it was moving before. Is that clear now? So that's why V1 is the new velocity of that body 1 that was moving. It's still almost equal. That's the name of this sign here. It's still almost equal to the velocity that it was moving with before. Because the object that it hits is insignificant to its mass. So it does not really affect its velocity. Is it clear? Let's look at case 2. Now, what will be V2? What will happen to V2? Now, V2, which is the velocity of this ball now, of this ball. What will be the velocity of this ball? Let's see what will happen. Now, if you plug the values in here, into this equation. So V2, that's the velocity of this body, will become 2 times M1. What is M1? The body I was moving. M1, which is the cannonball, that's 1,000, over times U1, that's times this U1, over 2 M1 plus, over M1 plus M2, which is M1, 1,000 plus M2, 1. That becomes 2 times 2 times 1000, that's 2000 over 1000 plus 1, still 1001. If you divide this, it's almost 2, right? It's approximately 2. So 2u1. So what does it tell you? That v2, this body 2 will move with double, or will move with approximately double the velocity of the cannonball. So it will move twice faster than this guy. Is it clear now? And that makes sense, right? Imagine something like that hits a ball on its path, along its path. The ball will fly off. Is that okay? With almost double the velocity. You see the equation is making sense now. So that's what we try to do with all of these equations. Now let's look at the last case. Tell me by yourself now in the comment section. Tell me what will happen with where our mass, our second mass, is very, very much greater than our first mass. This is a case where we are assuming that a ball is coming to hit a cannonball. Mommy, this one. So this is where a ball, that small ball now, is one hitting the cannonball. Tell me what will happen using these equations to show me that you have understood it. So now let us now see a case for moving masses. Let me pause the video and clean the board. Now let's consider a case of a moving target. So you know that the target that we saw the other time was stationary. So the object that we hit was stationary. Now the object you want to hit now is already moving. Okay, so this object is moving. Now what will happen? This object is moving, and the guy we also projected, or more like our projectile in this case, is also moving, and then they want to collide. Now what will be the case for a moving object? Our guy is moving here with u1, mass 1, our mass 1 is moving, and the guy we want to hit is mass 2 moving in this direction, u2, and they want to collide. Now what will happen? They are both on this surface. What will happen? Let's write since total linear momentum is conserved, given that the momentum is collision is elastic, we have that m1 u1, like we said, will be equal to what? Plus rather m2 u2 will be equal to m1 m1 v1 plus m2 v2. So if this is the case, then we know that the total kinetic energy also. Now let's rewrite this expression. This expression becomes m1 u1 rather. Let me bring this guy here. m1 u1 minus m1 v1 is equal to m2 v2 minus m2 u2. Now look at what I want to do here. See, I want to write this thing such that, you know, m1 is common here, m2 is common here. But I want them to look alike. This one is u before v. I want to make this one look like u before v also. So it will look like this. m1 u1, or like m1 is common between u1 and minus v1. No, let's write it in full. m1 v1 is equal to, watch, this will become minus m2 u1, m2 u2 plus m2 v2. If I wanted to write this, it will become m1 u1 minus m1 v1. Just be following me, you get it. Then minus equal to minus m2, minus into bracket m2 u2 minus m2 v2. Do you see now? I've changed the way the equation looks. So from here, I can then say that m1 I can now factorize. m1 is common between u1 and minus v1 equal to minus m2 is common between u2 minus v2. Is this clear? So by the time you open this bracket, you see it to give you this back. Is it clear? Now the reason why I manipulated it this way. Let's call this our new equation. I don't know the last equation there, so let's rename now. equation 1. Now, using KE, total KE is also conserved. Total KE is conserved, remember? So this becomes that half mv squared, half m1 u1 squared plus half m2 u2 squared should be equal to half m1 v1 squared plus half m2 v2 squared. It's mouthful. After this, we are going to look at inelastic collision, then we start solving questions. Is that clear? So you need to stick with me till the end of the video. God bless you as you do so. From here, I can bring this guy here also because they look like M1, M1. Bring that guy here. So it becomes half M1, pretty much like everybody has half. So let me divide through by half. If I divide through by half, half goes, half goes, half goes, half goes. So I have M1 U1 squared, bring this guy here, minus M1 V1 squared is equal to M2 V2 squared minus M2 U2 squared. Using the same idea, I want to write this one as U before V. This one too should be U before V. So that we have M1 is M1 U1 squared minus M1 V1 squared should be equal to minus M2 U2 squared plus M2 V2 squared. I want to write this so that U comes first before V, U comes first before V. So from here, M1 is common between U1 squared minus V1 squared is equal to minus M2 is common, right? Between U2 squared minus V2 squared. Is this clear now? So by the time this guy opens the bracket, it gives you what we have on top back. So from here, we have difference of two squares here, so that we have M1 into bracket U1 minus V1 and times U1 plus V1. I've showed you how this becomes, right? If you open this bracket, you get this back. It's equal to minus M2 into bracket U again, U2 plus V2 minus, let's use minus first, and U2 minus, plus V2. If you open this, you get this back. Alright, so from here, you'll notice that we have gotten another equation, equation 2. So using the same technique, we'll divide equation 2 by equation 1. Dividing equation 2 by 1, we have this M1 U1 minus V1. I have to rewrite it. U1 plus V1 is equal to minus M2 into bracket U2 minus V2, U2 plus V2 all over this M1 U1 minus V1 equal to minus M2 U2 minus V2. Okay, so from here, this takes care of this, this takes care of this, this takes care of this. This can also take care of this. So from here, minus has cancelled out. From here, we have that U1 plus V1 is equal to U2 plus V2. Now, here's the assignment. I want you to show me by that V2 first. We know that V2 will be equal to U1 plus V1 minus U2, right? What you will do is this. Take the same steps or the approach that I took. Substitute this guy into equation 2, into this equation, and substitute this guy and write an expression for V1 and substitute in equation 1. Now, show me what you will get. You will notice that the equation you will get, take note please. You will notice that the equation you will get will, if you reduce U2 to 0, in the equation you finally get, Reduce u2 to 0, you will see that you will get the expressions we had before for the two equations you will get. I hope you understand what I said. This expression, use this one to replace v2 in this equation. To replace v2. But the first thing you do is, you open the bracket, and you now replace v2 by all these guys. The moment you do it, you get an expression for v1. When you get an expression for v1, you will redo it, and you will get an expression for v2. How do you get an expression for v2? Sorry. You write this in terms of v1. Now, it now be v1 will be equal to v2 plus u2 minus u1. So by the time you do that, you will get an expression for v1. For that v1, you will now use it to substitute. You now take that value, that expression for v1. You now substitute for v1 in this equation 1. After opening the bracket and all. The expression you will get, the way I did that first one, will be such that if you reduce u2 to 0, make u2 become 0, it will revert to the expression that we got. It will validate the expression that we got when one body is stationary. The body that we want to target is stationary. Is that clear? So that's just what I wanted to prove to you. Now, let's go to inelastic collision then. Inelastic collision. Now, I've told you about inelastic collision. What happens with inelastic collision? What happens is this, and in case you did not get that thing I just said, text me on this WhatsApp number, +234 9021416307, to show you. You can screenshot what you did for me. I will help you set it right. Is that clear? But I want you to, when you actively engage in physics, in trying to manipulate equations yourself, it becomes fun. Yes, and physics is actually fun, okay? Now, like I said, in inelastic collision, we see that only momentum is conserved, not K. Kinetic energy is not conserved. Total kinetic energy is not conserved. Now, first, physically, how do we see inelastic collision? Physically speaking, inelastic collision is just any collision where, after the collision of the two bodies, they stick together and move with the same velocity. That's what inelastic collision is. They don't bounce off. So usually, when they collide, what will happen is they will move together. Of course, they will move in the direction of the one with larger momentum. Exactly. So, for example, if, the other day, I was running, you understand? I just hit a car on the road because I had a great momentum. I was able to move the car while I was still running. Do you understand now? So the point is that the larger mass, so actually, reverse will be the case for an ordinary human. If a car hits you, the car will be moving you. You understand? So that's an inelastic collision. Is that clear? Where the masses, the bodies do not separate after collision. They stick together and move together. Stick together, move together. All right, so that's inelastic collision. Now let's put it in mathematical terms. We know that in inelastic collision, let's first see where body 1, the target U2 is stationary. So where U2 is stationary, our equation will be like this, that M1U1 will be the only thing that will be starting. It will be equal to M1, they will stick together. M1 will move with a similar velocity as M2. So they will move with the same velocity. Do you understand? Like, if it's confusing you, this is what I mean. That M1V1 plus M2V2. This is clear, right? But the new velocity V1 will be exactly equal to velocity V2. So let's call both of them V. Is that clear? If that's the case, then M1U1 will be equal to what? M1V plus M2V. If this be the case, then M1U1 should be equal to M1 plus M2 times V. Is that clear? This will be equation 1. If you want to write this expression for V in terms of M, we have that V will be equal to m1u1 over m1 plus m2. So we are told to find the new velocity, common velocity. We call this V. This V is called the common velocity because this is the velocity with which the two bodies that have collided will move with. With which they will move. Now we know this. Now the next thing you want to see is, now that we know this, the next thing we want to see is, what about the energy? The energy. So for a system like this, where this force guy is stationary, kinetic energy, keep in mind, kinetic energy not conserved. So since the kinetic energy is not conserved, we can only check them separately. So we'll check kinetic energy before collision. So before collision, what did we have? The total kinetic energy, Ke, before collision will be equal to half, this was the only guy moving before collision, half m1u1 squared. Now how about after collision? After collision, this is what we now have, right? After collision, Ke becomes half m1 plus m2 v squared. Is this clear? Now what if the two bodies were moving? What if the two bodies were moving? Two bodies moving. The target and the projectile, both of them were moving at the beginning. Two bodies moving, or two moving bodies. Either ways, the initial momentum will be conserved, right? The total momentum is always conserved. So we have that m1u1 plus m2u2 will equal to what? m1v. Now, they will still stick together, right? That's the property of inelastic collision. So since they will still stick together, we'll still have that m1 plus m2 times v. You see, it didn't really change, only that we added this new guy that is moving also, the momentum of the new guy. Now, what will also happen in the kinetic energy before collision now? Ke before collision. So what will happen is that half m1u1 squared plus half m2u2 squared. Is that clear? Now, after collision, okay, there was something I wanted to tell you. Since kinetic energy is not conserved, it means that some energy is lost. Is that okay? So I'll show you the equation for calculating energy loss now. Now, momentum after collision, kinetic energy after collision is equal to what? Half. Now, since this thing will change, the bodies will move with different, they will stick together, right? They will stick together. So we'll have similar distance for the kinetic energy. But this is for loss in energy loss. I'm sorry. I wanted to show you energy loss, right? What will be the energy loss? Energy loss will basically be this formula minus either this or this. Is it clear? Either that or that. So that is energy loss will be equal to half m1 plus m2 v squared minus, am I correct? Yes. Minus, this is where the body is stationary. If the body is not stationary, if the body is stationary, we have m1u1 squared. If the second body is not stationary, it will be minus this plus this again. I hope you understand. So this is how you calculate energy loss. Is that clear? Now let's solve some questions. What is this? What is she asking for? Now let us consider these three questions. The first one says, a 6 kilogram mass moving with a speed of 4 meters per second. So M1 is 6 kilograms and it was moving with U1 of 4 meters per second. Collide with a body twice its mass. So M2 will be 2 times of this, right? 2 times 6, which is what? 12 kg. And moving at half its speed. So U2 is half this. U2 what? 4 meters per second. Now, along the same direction. So if it's along the same direction, then we have that after the collision, 6 kg body moves in opposite direction. So there's change in direction, right? With a speed of 2 meters per second. Find the final velocity of the heavier body. So the final velocity of this. So keeping in mind that total momentum is conserved, we know that M1U1 plus M2U2 will be equal to M1V1 plus M2V2. Half, that's 2. Half its speed along the same direction. Half its speed. Is that clear? So just restore power, please. Okay, so as I said, that this guy is moving, it has twice its mass and is moving with half its speed. So 2 meters per second. Then, so we have this expression. Now, they were moving in the same direction before collision. Once they collided, they now separated. Is that clear? So if that's the case, then M1, which is 6 times U1, that is 4, plus M2, 12 times U2 is 2. Is it clear? Now, equal to, the 6 kg body moves in opposite direction with a speed of 2 meters per second. 2 meters per second. Now listen, this new V1 now, V1 will be negative 2. Why? Because the same direction that we were moving together, we have accounted it as positive. So if we have taken it as positive, then any other direction will be negative, in which case that guy is negative here. So we have 6 times minus 2 plus M2, which is 12 times V2, which is what we're looking for. The final velocity of the heavier body. So if that's the case, this is 24 plus 24 is equal to minus 12 plus 12V. 12V2. Let this guy come here. We have 48 minus or plus 12 is equal to 12V. 12V2. Divide both sides by 12. Here 4, here 1. 4 plus 1, 5. So V2 is equal to 5 meters per second. So that's the answer. In case you don't know what I did, just use your own calculator, you get the same answer. So that's the answer. Now that's all it says we should do there. Let's do number 2. Number 2 says that 2 bodies X and Y of masses 8 kg and 5 kg moving towards each other with velocities 5 meters per second. So mass M of X, let's call it Mx, is 8 kg. Mass of Y, My, let's call it 5, that would be the one that is 5 kg. They are moving towards each other with velocities 5 meters per second and 3 meters respectively. That means that U sub X is 5 meters per second and U sub Y is 3 meters per second respectively. Collide with each other, they collide with each other. Assuming the collision is perfectly inelastic. So they collide with each other and the collision is perfectly inelastic. stick. I've told you physically, what does that tell you? That they will stick together. Stick together. Good. So you have to calculate their common velocity after collision. And what will be the total kinetic energy? So let's calculate their common velocity. Recalling that mxux plus myuy will move with mx plus my mu v. Is it clear? So if that be the case, we have that 8 times 5 plus 5 times 3 is equal to 5 plus 3, 8 plus 5 times v. So this times this 40 plus 15 is equal to 13v. Divide both sides by 13. Okay, we cannot divide through yet. 55 is 13v. So we need a calculator again. This will be 1351. That's 4. 52, right? Let me get a calculator, please. Alright, I'm sorry I couldn't get a calculator, so we have to manage what we have. You know that 4 times this is 12, no? So that's 3. 3 times this is 9, 39. 39 plus 13. That's 2 now. That's 5, yes. So 1, that's 52, yes. So that's 4. So that's 4 number 3 over 13. 3. 13 30, that's 2. So let's use approximately 4.2, please. So the answer is approximately 4.2 meters per second. Then, so this is their common velocity. It now says we should calculate the total kinetic energy of the system before and after collision. Before and after collision. So what will be the total kinetic energy of the body before and after collision? So before collision, you know kinetic energy is not conserved. So before collision, Ke will be equal to half m1, both of them are moving. So half mx ux squared plus half my uy squared. Now, that will be half, what is mx? 8 times what is ux? 25. Ux squared, that's 5, that's 25. Plus 1 over 2 my, that's 5. Times square 3, 9. Okay? So here 1, here 4. 4 times this, 100 plus half of this is 4.5. 45 times 5, 22.5. 2 to 5. So we have 22.5 equal to 122.5. So this will be joules. This will be the kinetic energy before collision. What about after collision? After collision, right? It said before and after collision. So after collision, it will become, what's this after collision? This half mx plus m sub y v squared. This becomes 1 over 2 into bracket 8 plus 5 times v squared, 4.2 squared. That becomes half of 13 times 4.2 times 4.2. I need a calculator. 2.1. So the answer will be 13 times 2.1 times 4.2. Put that in the comment section. The answer, please. Put the answer in the comment section. This is very bad. Let me check. Now, because of the absence of calculator, where I thought I was going to take this video to, might not be able to get there. So now, I'll quickly teach you something, because as I saw this question now, we'll need a new concept to be able to solve it. And that's the last concept I'll take you. That is coefficient of restitution. Now, I was supposed to still teach you the ballistic pendulum. That's what we use to calculate the speed of a bullet. Is that okay? Now, I will teach you in another video. So if you want me to release the video quickly, comment in the comment section below. And there's something I wanted to say. Okay, yeah, there's also collision. Oblique collision. I was also supposed to teach you that. So that one also I'll release it with that other guy, ballistic pendulum. I couldn't find a calculator, I couldn't find. Yeah. That's probably because I don't use calculator to calculate a lot. So I'm not used to taking it around. Alright, so I wanted to teach you coefficient of restitution. That's what you need to solve this guy. Coefficient of restitution. Now, what's coefficient of restitution? Coefficient of restitution is simply the ratio of the velocities before collision, the ratio of the velocity after collision, the velocity after collision to the velocity the relative velocities before collision. Mommy? Yes, ma'am. Amen, ma'am. So before collision. So now it's denoted by E. It is denoted by E. Now the formula is simple. The velocity after collision is V2 minus V1. And it's actually, we take the absolute values. So, and U1 minus U2. This is the formula for coefficient of restitution. So now if E is equal to 0, there are three possible values of E. E could be less than 1 and E could be equal to 1. When E is equal to 0, we have that the system is the collision is perfectly inelastic. If this guy is equal to 1, the collision is if the coefficient of restitution is equal to 1, the system is perfectly elastic. And if it's less than 1, it is just inelastic. Okay? Collision is just inelastic. Now, so you will use this to solve this question. I will show you what to do. It says the ball moving with initial velocity of this and due east collides with a similar ball of equal mass. So the masses are equal. So I'll tell you what to do. So of equal mass, moving with an initial velocity, this one, due west. So due west, the second velocity will be negative. Is that clear? Calculate the final velocity of the body if the collision is perfectly elastic. So what will be the value of E here? Perfectly elastic collision. E will be equal to 1. So what do? You take E equal to V2 minus V1 over U1 minus U2. So if that be the case, now what will V2 be? Is the new velocity of the body, right? So that is the final velocity you're looking for. Now V1 is also the final velocity of the other guy. Now, it is perfectly elastic now. It now says that, now how do you find U1? Yeah, some of you are already looking like we have two unknowns here. I'll show you what to do. You just watch me. U1 is the initial velocity of the first guy. That is 6. U2 U2 will be 3.5 meters per second. But remember, U2 will be negative. If we take U1 to be positive, U2 will be negative. Okay? By the time you plug this, and E is for parallel elastic, E value is 1, right? By the time you plug this into this equation, you have two unknowns. Now, you now make it quadratic, simultaneous equation by bringing our initial formula of M1 for perfectly elastic, M1U1 plus M2U2 equal to M1V1 plus M2V2. Now, keep in mind that M1 and M2 are the same. So you have that M into brackets U1 plus U2, since M and M's are the same, equal to M into bracket V1 plus V2. So from here, M can take care of M, and U1 plus U2, you now use the values. U1, 6, minus U2, which is minus 3.5. Is it clear now? You see that by the time you do this, you are going to get an expression for V1 and V2 that way. So use the two formulas. You will get an equation that you get simultaneous equation, and tell me your values for V1 and V2. Tell me your answers for V1 and V2. You understand what I mean? Yeah, M takes care of M, V1 plus V2. So just work your way around it and tell me your answer in the comment section. If you're unable to solve it, put in the comment section that I should solve it in another video. I will definitely do it, I promise you. I do have to subscribe to the channel, but it will lead me to use the calculator again, so that's why I'm not solving it. But I want you to try it on your own, okay? Oh no, someone is saying that I shouldn't do it that way. Okay. This plus this, that will be 6 plus 3.5 equal to V1 plus V2. So if we write an expression for V2, V2 will be equal to, this is 9.5 minus V1, right? That's the case there. Using this equation, let's call this equation 1. Using coefficient of restitution, 1 for perfectly elastic will be equal to V2, which you don't know, minus V1 over U1, which is 6, minus 3.5 again, right? So this becomes 1 equal to V2 minus V1 over 6 plus 3.5. So 1 becomes V minus V1 over 9.5. So from here you cross multiply. 9.5 will be equal to 9.5 will be equal to 9.5 will be equal to V2 minus V1. So from here, V2 will equal to 9.5 plus V1. So you can already see there are two expressions for V2 now. So V2 is this. So it means that 9.5 minus V1 is equal to 9.5 plus V1. Are you with me? So from here, 9.5 will come here. This one goes here. 9.5 minus 9.5 is equal to V1 plus V1. So that's 2V1. I hope we didn't make any mistake. Let me clean this part. Let me retry it. We don't need a calculator, in fact. Alright, so I'm looking at it carefully. I think this was where we made a mistake. So it will be 6 plus minus this. So it becomes 6 minus this. 6 minus this. Is that correct? Using this, right? So minus. That will be 2.5. That will be 2.5. So here we are saying that 2.5 is equal to V1 plus V2. So if we write an expression for V2, it should be equal to 2.5 minus V1. Okay. So what will now equate here? We wrote that expression for V2 from coefficient of restitution. V2 is equal to 9.5 plus V1, and the same V2 is equal to 2.5 minus V1. 2.5 minus V1. So we have that 9.5 plus V1 is equal to 2.5 minus V1. So from here, this one comes there, that one goes there. Oh no, let this one come here. V1 plus V1 is equal to 2.5 minus 9.5. So we have 2V1 is equal to this minus this. That will be minus 7. Minus 7. So divide both sides by 2 over 2. V1 becomes minus 3.5 meters per second. So you know what you will do to show me that you stuck to the end of the video? Use this to find the value of V2. Just substitute into any of the equations. Provided we call this equation 1 and this one equation 2. Alright, this will be it for this video. Do well to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. And as well, let me know your comments about the video and any other topic you want me to make videos on for you, or you want me to solve questions on. You can reach out to me on that WhatsApp number. God bless you.